Well, welcome back again to the second session of our short course in hypersonic aerodynamics, basics with applications. Before I get started, I have a certain matter to address. During the lunch break, I found out that there is at least one, maybe two remote sites that don't have the advantage of having the textbook as the course material in front of them right now. Let me point out to you, and we'll use the overhead camera just for a minute, that in the flyer that the AIAA put out in terms of the hypersonic aerodynamics basic and applied, under course materials, it stipulates that the text to be used is the textbook, and then we'll also be using, of course, general notes. The textbook we're using today, the general notes will be used tomorrow in the course. I want to apologize to those people who don't have in front of you the book, and again I'll put this on the overhead camera. I want to apologize for those of you who don't have the book in front of you, because as you can tell from our past discussion, that I'm taking material directly out of that book. For those of you who do have a copy of the book, it's a distinct advantage because you can sit there and look back and forth, look at the screen, look at the book, and so forth. For those of you who don't have the book in front of you, I'll do the best I can to take that into account for the rest of today. There'll be no problem at all beginning tomorrow morning, because then we are going into the AIAA notes that have been distributed by the AIAA. For those of you who don't have the book in front of you, let me say this, and this is being addressed to everybody as well. One of the objectives of a course like this is to break the ice for you, to give you something to think about, and also to help you a month from now or a year from now, whatever the case may be, to help you to give you an idea of where to find some material when you need to go back and find out something about it. And what I'd like to think is that the notes as well as the textbook for this course are going to be most useful from that point of view. The most use for this material is not to have it in front of you right this minute, but rather to have it available to you a month from now or a year from now or whenever you need it, so that you can go back and research and read more deeply into the material we're talking about, so that once you've seen this on the monitor and maybe a little bit of it is in your mind's eye, then you can go back and at a later date use the resource material, the textbook and the notes, to remind yourself about material we've covered, to look at it more in detail and learn about it more deeply. So once again, we will try the best we can this afternoon to take into account, for those of you who don't have the book, to try to pitch things in a way that it won't be too much of a compromise for you. For those of you who don't have the book in front of you, my advice to you is hang on, keep with it, and just simply, actually in a sense maybe there's some advantage. You can sit back and just enjoy what's on the screen if you want to do that, and get whatever out of the discussion it is that you can. And as I'll say again, the major aspect of having this material will come later on after the course is over, to give you something to refer back to. So hopefully by that time you will have the course material and you can use it in that vein. So we'll proceed ahead under those under this criteria. And how are we going to proceed ahead? Let's go back to our roadmap, see where it is that we are at. We are looking at, again, hypersonic inviscid flows. We are in the process now of we're going to start talking about something called flow field considerations. We have looked very quickly at basic hypersonic shock relationships. We looked at the local surface inclination methods. We're now going to run down this part of the roadmap dealing with flow field considerations. And to start that out with, when we're talking about flow field considerations, we first have to talk about the general governing equations. And this is, for example, we'll start out with, for those of you who have the book, section 4.2, the governing equations. Let's take a look at for an inviscid flow, let's take a look at the governing equations. The governing equations are these. The continuity x momentum, y momentum, z momentum, and energy equations for an inviscid flow. These are called the Euler Equations. I'm making the assumption that most of you have seen these equations somewhere before. They are simply statements that mass is conserved, force equals mass times acceleration, Newton's second law, written in 3 Cartesian coordinate directions, and the energy equation, which in this particular case is written as an entropy equation, because the type of inviscid flows that we're going to be dealing with here will be adiabatic inviscid flows. And for an adiabatic inviscid flow, we essentially have an isentropic flow along a streamline, and this equation is simply saying that the entropy of the flow is constant along a streamline. And that is used in a way as a substitute for the energy equation. Now, these are they're called the Euler equations. They are the governing equations for an inviscid, and written with the energy equation in this form for an inviscid adiabatic flow. Let's see what this system of equations tells us about certain aspects of hypersonic aerodynamics. Now, the first item that we're going to talk about is something called Mach number independence. Mach number independence. This begins and again in your book, section 4.3, and let's see what we mean by Mach number independence. I'm going to go back to previous figure that we looked at just a few minutes ago before the lunch break. Remember, this is a plot of pressure coefficient as a function of Mach number for both wedges and cones. And we use this to get a feeling for the accuracy of Newtonian theory. Let's use this figure in a completely different sense. Forget about the Newtonian theory for a moment. And just look at the pressure coefficient for a wedge and see how this pressure coefficient, wedge pressure coefficient, varies with Mach number. Notice, out here at low Mach numbers, Mach 1, Mach 2, Mach 3, the pressure coefficient is varying like mad. But then around Mach 5, it plateaus out. And from Mach 8, 9, 10, 11, 12, the pressure coefficient is essentially the same. There's a type of independence there that comes in at high Mach numbers. It's an example of what we call Mach number independence. For the wedge pressure coefficient, the same thing happens for the cone pressure coefficient. There's a Mach number independence. And this is characteristic of many properties of hypersonic flows, that if you get to a high enough Mach number, and maybe that high enough Mach number may be Mach 6 or Mach 7, when you increase the Mach number above that, certain characteristics don't change very much anymore. They become relatively independent of Mach number. Now, let's take a look at the mathematical underpinnings of that. What do? Let's go back to our Euler equations, which we were just looking at. If these Euler equations now are non-dimensionalized, and I'm going to quickly show you how they're non-dimensionalized, and again, keep in mind that this is a qualitative discussion. We're not going to spend any time on equations, and I don't expect you to remember any of these, but I want you to get a feel for the fact that if the independent and dependent variables are non-dimensionalized, say by dividing distances by the length of the vehicle and velocities, by free stream velocities and pressure by rho infinity, v infinity squared, and so forth, the Euler equations in the non-dimensional form become these. Now, there are non-dimensional equations. These equations must be solved in the presence of, or in conjunction with, boundary conditions. Let's take a look at the boundary conditions. First of all, along the surface of the body, the flow must be tangent to the surface of the body, always. In an inviscid flow, the flow must be tangent. This should be a fairly familiar boundary condition then. This says that the vector velocity dotted into a unit normal vector perpendicular to the surface evaluated at the surface must be 0. That tells you the velocity is tangent to the body. If you split the unit normal vector up into x, y, z components, that boundary condition becomes this equation right here, equation 413. And some of you may recognize the nx, ny, nz as being nothing other than direction cosines. Then we non-dimensionalize the velocities, and we get this as our body boundary condition. Then finally, we take the properties behind the shock wave, because the body is one boundary for the flow. The shock wave can be viewed as another boundary for the flow. And if we deal with our shock relationships in terms of the non-dimensional quantities we were just looking at, the shock wave equations, the non-dimensional shock wave equations become this. These are applied on the boundary right behind the shock. Now, the point of all of this is as follows. Let's ask ourselves a question. We're going to drop down here. We're going to ask a question. Where does the Mach number explicitly appear in these equations? Well, let's go back and look. Here are our original governing equations, the Euler equations. Let's look. Here's the non-dimensional values. Here are the equations. There's no Mach number in there, is there? Where does the Mach number appear? Well, let's go look at the boundary conditions. At the body boundary condition, equation 414, Mach number, no Mach number there, it's not appearing. Let's look at the shock boundary conditions, these equations right here. Where's the Mach number? There it is. It's just in the boundary condition. Okay, so that's the answer. Only in the shock boundary conditions. Next question. If we go to the limit of very high Mach numbers, these shock wave relationships approach these, in terms of the non-dimensional quantities, approach these values. Now let's ask the question. Where does the Mach number explicitly appear in these equations in the high Mach number limit? Well, we don't see any Mach number there. We don't see any Mach number again in the governing equations. We don't see any Mach number in the body boundary condition. Answer, no place. The Mach number appears no place. Conclusion, at high Mach numbers, the solution of these equations must be independent of Mach number. And this is the mathematical underpinning of the principle of Mach number independence. This is why, when you go back, and we'll repeat this, we'll look back at our previous figure. This is why, when we look at the pressure coefficient as a function of Mach number for a wedge or for a cone, and it would be for virtually any hypersonic shape, you find the pressure coefficient becoming independent of Mach number at high Mach numbers. Furthermore, we can look further at Mach number independence. We're looking at figure 4.1. This is a plot of the drag coefficient as a function of Mach number for two different shapes of bodies, a cone cylinder and just a sphere. The drag coefficient is plotted as a function of Mach number starting from 0 and going out to Mach 10. These are experimental measurements made in a ballistic range. Notice what happens. Let's look at this sphere for a minute. Sphere starts out here at this drag coefficient at essentially Mach 0 and rapidly increases. Now, by the way, why does the drag coefficient rapidly increase as we get near Mach 1? Anybody know? We're getting essentially the beginnings of shock waves. We're getting transonic flow. This is, some of the aerodynamicists in the audience will recognize this as the transonic drag rise. Has nothing to do with hypersonics. But then as we go beyond Mach 1 and we go to higher Mach numbers, the drag coefficient actually reaches a peak and then starts coming back down. But then it plateaus out. And look at this. The experimental measurements for the drag coefficient for the sphere are relatively independent of Mach number. A graphic example of Mach number independence. Very important, a very important quantity. We will see examples after examples in hypersonic aerodynamics of this Mach number independence existing, and it's important for us to recognize that it does exist, and it's not just a fluke. It is something that you can actually mathematically justify just by inspecting the non-dimensional governing equations. Okay, so that's all I'm going to say for the time being anyway on Mach number independence. Let's go to our roadmap once again. Here we are in the flow field considerations. We've just mentioned Mach number independence. Something else prevails in hypersonic aerodynamics, something called hypersonic similarity. Let's take a look at that for the next few moments. Hypersonic similarity. Hypersonic similarity is predicated on something called the hypersonic small disturbance equations. The hypersonic small disturbance equations are obtained from the governing Euler equations, which we were just looking at a few minutes ago. These were our original governing Euler equations. And by replacing the velocities in these Euler equations with a slightly different point of view, namely substituting for our velocities perturbation velocities. And the picture is this. Imagine that we have a velocity. It doesn't have to be just on the surface of the body. It can be anywhere out in the flow field. Let's resolve that velocity into a horizontal component. And let's say that the horizontal component is equal to the free stream velocity plus some change. That change is called u prime. That's called the perturbation velocity. The vertical component of velocity is equal to the free stream component, which is 0, plus some change, and that's v prime. These u primes and v primes are called perturbation velocities. You can construct you can put those into the governing Euler equations, which we have here back, and again I'll refer to that. Put in the perturbation velocities into the governing Euler equations, and at the same time non-dimensionalize the quantities as seen here. And for those of you who have the book, that's on page 87. For those of you who don't, just look at this for a minute. We non-dimensionalize the quantities again, dividing by L. We'll take the y bar and divide that by L times tau. Tau is now this slenderness ratio that I defined earlier, and I'll write that down again. Tau is just, say, a base diameter of a body divided by the length of the body. If we not only put in our perturbation velocities, but non-dimensionalize the quantities that we see here, and if we make the assumption, the additional assumption, that the slenderness ratio is small, then we obtain a system of equations which are called the hypersonic small disturbance equations. And let me write that off here on the side. These are the hypersonic small disturbance equations. They are the governing equations for the flow over a slender hypersonic vehicle at hypersonic speeds, a slender hypersonic vehicle. And there's something very interesting about these equations. What is interesting about them? Ask yourself the question, where the x component of the perturbation velocity appears. If we go back and look at this picture, the u prime, the x component, the x perturbation velocity, where does that velocity appear in these equations? And the answer is only in one equation. This is the x momentum equation. Here's our continuity equation, x momentum, y momentum, z momentum, and energy equation. And the velocity component u prime appears only in this one equation right here. All the other equations do not have a u. This is characteristic of the flow over a slender hypersonic vehicle. Namely, that the x momentum equation is decoupled from the rest of the system. And there's a reason for that, a physical reason for that. And I'm going to refer back to something we looked at much earlier in our first discussion, going all the way back to looking at our flow field properties across an oblique shock wave, and looking in the hypersonic limit at these equations. And in particular, looking at, for example, the u2 velocity. The u2 velocity is a horizontal component behind the shock. The v2 is the vertical component behind the shock. This equation in the hypersonic limit, simply saying that the change in the horizontal component of velocity across the shock varies as the square of the wave angle. Varies as the square of the sine of the wave angle. Whereas the vertical velocity varies just basically as the sine of the wave angle. Conclusion: if you have a slender body where the wave angle is small, the sine squared is going to be a very small value. And conclusion is that the change in the horizontal component of velocity is much smaller than the change in the vertical component of velocity. Now, let's look up here for a minute. Here is a slender hypersonic vehicle. And what we've just said is that when you look at the physical aspects of the flow over that slender hypersonic vehicle, that the change in the velocity perpendicular to the body, vertically in the flow, is going to be much stronger and much more meaningful than the change in the velocity in the flow direction. And therefore, on a physical basis, it makes sense then for the x momentum equation in the hypersonic small disturbance equations to be decoupled from the rest of the equations, because the change in the velocity in the horizontal direction is not very large in the hypersonic flow over a slender body. Now, these equations that we were just looking at, these equations are the governing equations for the flow field over a slender hypersonic body. These are the equations that are used to demonstrate a type of hypersonic similarity. And let's take a quick look at that. Our next subject, just for a moment here, something called hypersonic similarity. What is the principle of hypersonic similarity? Well, if we take our governing equations, and we'll put them back on just for, again, to try to cover all the bases. If we take these governing equations and look at the corresponding boundary conditions using these same non-dimensional variables, boundary conditions, for example, behind the shock wave, we will get equations that look like this. The velocities, and what appears in this equation? A Mach number times a slenderness ratio. What appears in this shock wave equation? A Mach number times a slenderness ratio. What appears in the equations for pressure? A Mach number times a slenderness ratio. So in the boundary conditions for which these equations are solved, the Mach number doesn't appear by itself, neither does the size or shape of the body appear by itself, only the product of the Mach number times the slenderness ratio. That's what appears. And so that tells you that the solution of these hypersonic small disturbance equations, these equations right here, depend only not on the Mach number by itself or the slenderness ratio by itself, but only on the product of Mach number times the slenderness ratio. And that is why this product of Mach number times the slenderness ratio is called the hypersonic similarity parameter. Because, and look at me again now, what this is saying is this, that the solution of those governing equations for this body with a certain slenderness ratio at a given Mach number in a given wind tunnel will be the same as the solutions of the flow field over this body that has a different slenderness ratio in a different wind tunnel at a different Mach number if the product of m infinity times tau over here is the same as m infinity times tau over there. That is the essence of what is meant by hypersonic similarity. Now, the proof, let me show you the proof of the existence of hypersonic similarity. Let's look at some actual results. And by the way, before I do that, let me quickly point out that effectively what we're saying here, equation 458 is saying this, that the pressure coefficient divided by tau squared becomes a function of just the non-dimensional space, the hypersonic similarity parameter, and if you have an angle of attack, alpha over tau. So it's Cp over tau squared that is independent, that is just a function of m infinity times tau. If we integrate the pressure coefficients to give us lift and drag coefficients, we have this result. We get a lift coefficient over tau squared as a function of the hypersonic similarity parameter, and the drag coefficient over tau cubed is a function of the hypersonic similarity parameter. All of this information is given in the reading material, and later on at your leisure, when you get a copy of the material, or if you already have a copy, please make sure to read through this to see where all this comes from. Now, by the way, these are lift and drag coefficients reference to the planform area of a body. If you reference the lift and drag coefficients to the base area of the body, then what is a function of the hypersonic similarity parameter is the lift coefficient over tau by itself and the drag coefficient over tau squared. Now, let's very quickly look at what's going on here. Here is a plot of the pressure coefficient as a function of distance along the nose for two different bodies, they're both ogive cylinders. They have two different slenderness ratios and at two different Mach numbers. But the Mach number and the slenderness ratio are such that when you multiply the two together, you get a half. So the hypersonic similarity parameter is the same between these two bodies. What is plotted here is the pressure coefficient over tau squared as a function of distance along these bodies. Non-dimensionalized distance, percentage of the nose length. And what do we see? These are calculated results based on the method of characteristics. And we see that Even though the Mach numbers are different and the slenderness ratios are different, when you have these two sets of calculations, they all fall on the same curve. It is a graphic demonstration of hypersonic similarity. Now, just an elaboration on this for a minute. All of you who have studied fluid dynamics know that there is such a thing called dynamically similar flows. We all know how to create dynamically similar flows. Dynamic two flows, if we have two different flows, and I'll hold these things up again, if we have two different flows over different bodies, if the bodies are geometrically similar, and if in these two different flows the Mach numbers are the same, and the Reynolds numbers are the same, and the Prandtl numbers are the same, and so forth. Those principal things, if those principal things which we call the similarity parameters, if they are the same between these two different flows, then the lift coefficient for this body will be the same as the lift coefficient for this body. The drag coefficient for this one will be the same as the drag coefficient for this one. That's the essence of dynamic similarity. Now, when we talk about hypersonic similarity, we're not saying that this dynamic similarity doesn't exist. Indeed, it does exist for hypersonic flow as it exists for any kind of flow. That type of dynamic similarity does exist for hypersonic flow. It holds for all types of flows. What we're talking about here, when we're looking at hypersonic similarity, when we go back to this figure, for example, and we plot pressure coefficient over tau squared for the same m infinity tau, what this is an additional consideration that is superimposed on our similarity arguments that holds just for hypersonic flow and just for slender bodies. So please keep in mind that when we talk about hypersonic similarity, we're talking about something that is an extra, additional, overlaid consideration that is separate from the original consideration, the basic consideration of dynamically similar flows. It's an extra advantage, if you wish. It's an extra advantage associated with hypersonic flows that you can establish this extra type of similarity in addition to the other type of general dynamic similarity. Okay, just want to let you know that that exists. And that's all that we're going to say about hypersonic small disturbance theory, hypersonic similarity. Hypersonic similarity is based on hypersonic small disturbance theory. Now, there are other aspects dealing with flow field considerations. Let me quickly bring out another particularly interesting aspect of hypersonic flow. There's something listed here called blast wave theory. Let's take a look at what is meant by blast wave theory. First of all, a little bit of mathematics. Let's go back to our original Euler equations. We started out this particular discussion by looking at the governing equations for inviscid hypersonic flow. Inviscid hypersonic flow. These are the governing equations. Notice that they are for an unsteady flow because we have time derivatives here. Okay. Now, let's just write these equations for an unsteady two-dimensional flow. If I take these equations and write them for an unsteady two-dimensional flow, the dimensions being in the y and z directions, then I get this system of equations right here. So these are, now put them side by side more or less, our governing Euler equations are these equations right here. If you write them in the y and z direction, then they become simply these equations here. These equations govern an unsteady flow in two dimensions. So now let's look at these equations for just a few moments. First of all, let's non-dimensionalize the equations. According to what is shown there, that will be our non-dimensional equations. These are non-dimensional values. If we non-dimensionalize the equations with these non-dimensional values, we obtain the following governing set of non-dimensional equations. These are the Euler equations. Nothing magic about this. Now, I want you to look at this set of equations with one eyeball. We're going to put on the screen beside it as best possible. And I'll even fold the sheet here to allow us to do this. The hypersonic small disturbance equations. If we look at the hypersonic small disturbance equations And we look at these equations here for an unsteady two-dimensional flow. And if we blot out the uncoupled equation, the x-momentum equation, then we have four equations here which are mathematically identical to these four equations here. The terms are exactly the same. Just have little somewhat different symbols. We have a tau bar here and we have an x bar there. But these are identical equations. What do we have? These equations here, the hypersonic small disturbance equations, govern a three-dimensional steady flow over a hypersonic vehicle. These equations govern an unsteady two-dimensional flow. And yet they're identical equations. Conclusion, on a mathematical basis, there is an equivalence between an unsteady two-dimensional flow and a three-dimensional steady flow. Or maybe a more general way of saying it, there is an equivalence between a steady hypersonic flow and an unsteady flow in one less dimension. And this is the essence of something that is called the hypersonic equivalence principle. And what it means physically is the following. Let me show you what it means physically. It means this. Let's take a look, first of all, at a hypersonic vehicle flying through the air. Let's imagine that this hypersonic vehicle is flying along here from right to left with velocity v infinity, and that this hypersonic vehicle penetrates a vertical plane. Now this vertical plane is like a sheet of paper that's perpendicular. Whoops. Take the sheet of paper, put it perpendicular to the page there. There's our perpendicular plane, and this hypersonic vehicle is penetrating this perpendicular plane. Okay, the nose is just touching it there. A few moments later, the vehicle's penetrated this plane. The nose is this distance, v infinity times t1 downstream. And a few seconds, say moments later, it's this far downstream, and this part of the body is penetrating that perpendicular plane. Now, if we go back to this perpendicular plane and look at the picture of what's happening in this perpendicular plane, I'm going to take this perpendicular plane and put it flat. And this is what we see when you look at that perpendicular plane when we put it flat. In this picture, the nose of the body is just touching the plane. At a slightly later time, time t equals t1, the nose of the body has penetrated the plane, and what the plane sees is the cylindrical cross-section of the body, and it sees the shock wave of the body out here. At some later time, this perpendicular plane is seeing the body now this cross-section, and the shock wave is out here. Now, if we look at the right-hand side, what are we looking at? We're looking at an unsteady flow in two dimensions. We're looking at what you would see if you had an expanding piston in this two-dimensional plane, expanding out in the radial direction and driving a shock wave in front of it as a function of time. You're looking at an unsteady flow. And this unsteady flow is directly equivalent to the steady flow of this three-dimensional hypersonic body. This is the physical significance of the equations that we were just looking at earlier, the equivalence between a three-dimensional hypersonic flow and an unsteady flow in one less dimension. Now, a corollary to this hypersonic equivalence is this. It's called the Blastwave Corollary. Let's use the same philosophy but a little slightly different vein, in a slightly different vein. Here's a blunt nose body, like a blunt nose cylinder. It's coming in and it's impacting a perpendicular plane, like we have here, a perpendicular plane. It blasts its way through that perpendicular plane. At later times, this is what it looks like. Now, let's take this perpendicular plane, and let's put it flat, and let's look at what's happening in that plane. What's happening in that plane is this. The nose of the body touches the plane. The body is flying at something like Mach 25. It's as if that nose literally blasts its way through the plane, creating, therefore, something we can call a blast wave. And visualize that as a localized point release of energy in this plane right there. When you have that localized point release of energy, it will drive a blast wave in front of it as a function of time. This is an unsteady two-dimensional flow. There is an equivalence between this unsteady two-dimensional flow and the three-dimensional steady flow over this blunt nose body. Now, what's the advantage of this equivalence? The advantage is this. This flow field is not a particularly easy flow field to calculate. You have to use modern computational fluid dynamics predominantly to calculate this flow. This flow field is a classic solution you can find in the library. An unsteady blast wave solution. First unsteady blast wave solutions are carried out by G.I. Taylor. You can find them in the Royal Society back around 1948 or somewhere slightly after World War II. Obvious driving reason for it is to look at what happens to the blast wave from a nuclear blast. But these solutions lend themselves to what we call similarity solutions, and they exist in the library. They existed in the library back in 1950. And so those people carrying out hypersonic aerodynamics in 1950 recognized, or in the 50s, recognized that there was this equivalence. And you can use these solutions you can find in the library to give you some information for the flow field over this type of hypersonic body. This is a blunt nose cylinder. It's like this pointer, this pen, this object I'm holding in my hand right now. This is a blunt nose cylinder. You can use the same equivalence for a blunt nose slab. Let's take a look at this. A blunt nose slab is something like this book that I'm holding in my hand, this book which some of you out there don't have. This is a slab with a blunt nose in it with a flow going in this direction. Now that's a two-dimensional steady flow. That two-dimensional steady flow, which we now can look at here in figure 413, is equivalent to an unsteady one-dimensional flow, where the nose touches a perpendicular plane. That in the plane itself, there's the line where the nose is blasting through the plane, and there's a line release of energy which forces a blast wave in the upward and downward direction. So this is a two-dimensional steady hypersonic flow equivalent to an unsteady one-dimensional flow. You can find this solution in the library. Now, what can that solution do for you? You take those unsteady solutions and you replace the energy with nose drag, because that's what the nose drag is, what is supplying the energy in this picture. And you can replace the time, basically the time that appears in those answers with this relationship right here, which is simply saying that x is equal to v infinity times t. In other words, the x location on the body is equivalent to a given time in the unsteady flow. Replace this equivalence in the library solutions that you find, in the solutions you can find in the library for this unsteady flow, and you will arrive at useful expressions for the pressure distribution over the surface of blunt nose bodies that are called blast wave results. I'm going to show you what some of these solutions look like. Equations 4, 156, and 157 on page 129. Pressure ratio, P over P infinity, pressure on the surface of the body divided by the free stream pressure. For a blunt nose flat plate, I'll remind you again what that is. Blunt nose flat plate is like this book with a blunt nose on it. The blast wave solution says that the pressure varies inversely as x to the 2/3 power from blast waves. It says that the shock wave shape varies as x to the 2/3 power. There are various degrees of theoretical approximation you can use here. First approximation neglects the pressure in front of the blast wave. Says that the blast wave is so strong, the Mach number is so large that you can neglect the pressure in front of the blast wave. A second approximation takes into account the free stream pressure in front of the blast wave. And you get slightly different results, but the same variations, x over d to the x to the 2/3 power and x to the 2/3 power appearing both in the pressure and in the shock shape equations. Those are for a blunt nose flat plate. The equations for a blunt nose cylinder are very similar looking. Again, a blunt nose cylinder is like this pen with a blunt nose on it. Pressure varies as inversely as x. The shock wave shape varies quadratically. It's a parabola, x to the 1/2 power. Second approximations are slightly improved, but essentially the same. These equations that you're looking at are equations that allow you to calculate the pressure distribution over blunt-nosed axisymmetric bodies like a blunt nose cylinder or a blunt-nosed blunt leading edge wing, like a slab, like that book with a blunt leading edge. Let's see how good these equations are. These are examples of what's called blast wave theory. Let's see how good these are. I'm going to just show you one example. There are other examples. I'll just show you one. Here's a result for a blunt nose flat plate. This is a pressure distribution as a function of distance. The symbols here are wind tunnel data taken at AEDC, Mach number 8. And the dashed line, right, we see right here, is from our first approximation, is from this equation right here that says x varies as inversely as a 2/3 power. And you see the dashed line isn't all that great. But the second approximation, which is the dashed dotted line, is up here. The shape of that curve is much closer to the shape of the experimental data. That's this equation right here. Is much closer to the shape of the experimental data, but it's displaced upwards. So what do you do if you're an engineer? You want to grab hold of that curve and you literally want to shove it down to the experimental data. And how do you shove it down? You put in a virtual nose, leading edge nose location. You shift your x-coordinates by 2/3 of a body diameter upstream, and you get very nice agreement with the experimental data. And that makes sense, because let's go back and look physically at what we're doing. We're visualizing, in particular in this case, we'll use the book since we have a blunt nose slab. We're visualizing a hypersonic body shaped like this, blasting its way through the atmosphere, blasting its way through this perpendicular plane. And we're trying to symbolize that effect with an instantaneous energy release. And in fact, that's not happening instantaneously. The nose has a finite extent. And so it kind of makes sense to adjust these blast wave results, which assume an instantaneous energy release, by something that would account for the real dimensions of the nose, like maybe going a fraction of a nose diameter upstream to start your calculations at. But that is the essence of what blast wave theory is. Let me give you a recent application, show you a recent application of blast wave theory for the space shuttle. We're looking, and we've hopped over, for those of you who have the book, we've hopped over to page 138, and we're looking at the space shuttle. We'd like to quickly estimate on the back of an envelope, using a hand calculator, the pressure distribution along the bottom surface of the space shuttle, say at Mach 21 at 40 degrees angle of attack. Now, today we'd use modern computational fluid dynamics to make that calculation. But you are given the job of doing this in about 2 or 3 minutes on the back of an envelope. What would you do? Well, let's use the blast wave theory result for the pressure coefficient, and you have to accept this. We will assume that the space shuttle is kind of like a blunt nose cylinder, where the pressure coefficient varies inversely with x from blast wave theory, and this number comes from the blast wave theory. We will add to it the angle of attack result using Newtonian results, 2 sine squared alpha, to give us an equation for a 40-degree angle of attack for the pressure distribution as varying inversely with x, from this term from blast wave theory, this term from the Newtonian approximation. And let's take this curve, let's take this equation and plot it. Pressure coefficient as a function of x, plotted on a piece of graph paper. Here we are. That's this solid line right here. This is the pressure coefficient as a function of distance x, using a combination of blast wave theory and Newtonian theory. Now, superimposed on this curve are actual experimental data, results from the third and fifth flights of the space shuttle, space transportation system. And what do we see? We get very excellent agreement between this back of the envelope calculation using blast wave theory and Newtonian and the actual flight test data. It's just an indication in this world, I'll toss this out and we'll make the statement and then we won't say anything more. In this world of modern computational fluid dynamics, where people are using computers day in and day out to go through detailed flow field calculations, it is worthwhile to keep in mind that there does exist out there very approximate hypersonic types of relationships that allow you to make engineering predictions and back-of-the-envelope calculations, which sometimes are pretty darn good. And this is one example of that. So blast wave theory is a theory that was developed back in the 1950s for applications to hypersonic flow, and is just as good today as it was back in the 1950s. Now, very quickly, I mentioned computational fluid dynamics. Let's go back to our flow field considerations. And let's take a quick look at how we would do things in a more accurate way. All of our discussions here so far, Mach number independence, hypersonic similarity, blast wave theory. I'm not going to say anything about thin shock layer theory. We're going to pass over that. All of these have been kind of based on the approximate equations. Let's now go to the exact equations. Go back to the original ones we looked at the beginning of the discussion, our Euler Equations on page 78. Let's now tackle the solution of these equations exactly. And the first one that we will tackle, by the way, this is under the category now, we'll put this on the overhead, hypersonic inviscid flow fields, exact methods. One of these exact methods that has been frequently used is the method of characteristics. I'll only briefly mention that the method of characteristics is an exact solution for supersonic and hypersonic flows. It's just as useful for hypersonic flows as it is for supersonic flows. Let me point out to you an aspect of these flows, particularly an aspect to be used in the method of characteristics, a physical aspect of hypersonic flow. If we have hypersonic flow over a curved body, either a slender body and especially a blunt body, the shock wave supported by that body will be curved. And any time you have flow going through a curved shock wave, we mentioned it earlier this morning, if you take a streamline like the streamline 1, goes through a stronger portion of the shock, the entropy increase across that shock wave is a certain value. If we look at streamline 2, going through a weaker portion of the shock, the entropy increase for that streamline is less. Therefore, the entropy along streamline 2 will be less than the entropy along streamline 1. Same thing applies up here for a slender body. But as long as you have a curved shock wave, you'll have different entropies along the different streamlines. This creates a flow field that has entropy gradients. The entropy gradients are directly related to vorticity in the flow. For those of you who may remember, the fluid dynamic concept of vorticity has to do with the tendency of fluid elements to basically have angular velocity. And when you have entropy gradients in your flow, you have what is called a rotational flow, a flow with vorticity. This is in contrast to an irrotational flow where the vorticity is 0. Let's take a look at the vorticity generated in the flow field over a blunt-nosed body at hypersonic speeds. We're looking here now at figure 5.2. And what we're looking at is the plot of vorticity. We're looking at the flow over a blunt-nosed body. And here's the shock wave over that blunt-nosed body. And we're looking at a plot of the vorticity, which is the curl of the velocity, as a function of the wave angle, starting out here at 90 degrees where we have the normal shock, and then moving along the surface of the shock wave. Notice what happens to the vorticity. It goes up, reaches a maximum in around the sonic point on the shock wave, and then drops back down. Look at what happens to the vorticity. This is a value for a low Mach number 2. Look at what happens to the vorticity when you increase your Mach number. Mach 3, Mach 5, Mach 7, Mach 10. Tremendous amount of vorticity behind that shock wave. Conclusion, you have to solve your hypersonic flow field assuming that you have a rotational flow. You cannot assume an irrotational flow field. And if you wish to solve a flow field using the method of characteristics, then you have to use what is called the rotational method of characteristics. Very quickly, give you an idea of how the characteristic method works. The characteristics method, if we have a body shaped like this, you have a shock wave and you have a body, and you cover the flow field between the shock with a characteristics net, and you solve basically the Euler equations along this characteristic net. They're in the form of what's called compatibility equations. So when we're talking about exact methods for solving hypersonic flows, the characteristics method is one such exact method. Let me show you some results from the method of characteristics. Very quickly, we will look at flow over a blunt nose cone. These are calculated results calculated by John Rakich back in the late 70s. The blunt nose portion we haven't talked about how to calculate yet, but the portion of the flow downstream of the blunt nose is calculated by the method of characteristics. Here we are looking at a shock wave shape over a blunt nose cone at an angle of attack. The angle of attack is 10 degrees. The Mach number is 10. And the shock wave shape, here's the body, here's the shock wave shape above the body at 10 degrees angle attack on the leeward side. Here's the shock wave shape when you go 90 degrees around the body. Here's the shock wave shape when you go 180 degrees beneath the body. The shock wave shapes are all calculated by the method of characteristics. They agree very nicely with experiment. Good example of how useful the method of characteristics is for making hypersonic flow field calculations. There is, if you would look carefully at these shock wave shapes, I'd like to point out to you that you would actually find an inflection point and a local minimum in the shock wave and the shock angle. This is a plot of beta, the shock wave angle, as a function of distance along the body, let's say x. And if we look at the shock wave up above the body, that portion of the shock above the body, you'll see that the wave angle decreases as you go around the body. It reaches a local minimum and actually increases again. There's an inflection point in the shock wave shape. This leads to, if we calculate the pressure distribution over the surface of the body, figure 512, a pressure distribution that has an inflection point and a local minimum in the pressure distribution. These are characteristic calculations, and they demonstrate, I'm using this as a double barrel thing to show you results from the method of characteristics, and also to show you that in some hypersonic flow field patterns, flow fields, especially those associated with blunt-nosed axisymmetric bodies, you actually can get an overexpansion as the flow, as you go around the nose and flow downstream. The flow actually expands to a low value, lower, nature says, gee, I've overexpanded, and you actually recompress back up to a higher value. This is something that is characteristic of high-speed hypersonic flow fields over blunt-nosed axisymmetric bodies. Okay, we have 1 minute to go. Let me point out to you that there are other detailed computational fluid dynamic flow field calculations that we can use for a blunt-nosed body. I'm going to defer that, and as soon as we start up at the end of our, we're going to take a 10-minute break, and as soon as we start up again, I want to refer to some computational fluid dynamic solutions over blunt-nosed bodies, and then we're going to go into viscous flows. So let's take our 10-minute break now, and we'll see everybody back at 1:35.